Welcome to Gradient Canvas. Today we're going to learn about logistic regression and the sigmoid, how we turn a straight line score into a probability and classify with it. Last time we fit a straight line to predict a number, but so many of the questions we actually care about aren't numbers, they're yes or no. Is this email spam? Will this patient test positive? Did the student pass? The honest answer to those isn't yes or no, it's a probability somewhere between 0 and 1. So here's the problem. A straight line shoots off to plus and minus infinity. How do you get a line to predict a probability that politely stays between 0 and 1? You might think just fit a least squares line anyway and read it as a probability. But it breaks in two ways. First, it predicts nonsense. Probabilities like minus 0.3 or 1.4, which don't mean anything. And second, it's fragile. Add one far-off example and the whole line tilts to chase it, dragging the boundary for everyone else. We don't want a line that predicts values. We want one whose output is always a valid probability. The fix is one beautiful function, the sigmoid. Written sigma of z, it's 1 over 1 plus e to the minus z. Forget the formula for a second and just watch its shape. Feed it a very negative number and it hugs 0. Feed it a very positive number and it saturates at 1. And right at 0 it passes through exactly 1/2. It's a smooth S-shaped switch that takes any real number on the whole line and gently squashes it into the range between 0 and 1, exactly where a probability lives. Now we can build the model, and it's just 2 steps. Step 1. Take the same linear score we know from regression, w times x plus b, call it z. This can be any real number. Step 2. Push that score through the sigmoid. Out comes p, a probability. And be precise about what p means. It's the model's estimate of the probability that the label is 1, given the features x. So logistic regression is nothing more than a linear score, squashed into a probability. As the score slides along the line, that probability rides smoothly up the S-curve. Big positive score, high probability. Big negative score, low probability. A score of 0, a coin flip. Here's the part that surprises people. To actually decide yes or no, we threshold the probability at 1/2. But look, the sigmoid crosses 1/2 exactly when its input z is 0. So predicting yes whenever p is at least 1/2 is identical to predicting yes whenever the linear score wx plus b is at least 0. And wx plus b equals 0 is just a straight line. So even though the probabilities curve, the boundary between the two classes is perfectly straight, a line in 2 dimensions, a flat plane, and more. Watch it sweep as the weights change. It shifts and rotates, but it never bends. So if the sigmoid squashes the score into a probability, what is the score really? Invert the sigmoid and you get a gorgeous answer. Z equals the log of p over 1 minus p. That ratio is the odds, like 3 to 1, and its logarithm is the log odds, which has a name, the logit. So the linear part of logistic regression isn't predicting the probability directly, it's predicting the logit on a scale that runs from minus to plus infinity, which is exactly why a straight line is the right tool there. As the probability climbs, the odds multiply and the log odds march up in even steps. And this clears up the most confusing thing about the name. It's called regression because, under the hood, it really is doing linear regression, just on the log odds instead of on the raw label, and only then squashing to a probability and thresholding to classify. Each weight shifts the log odds. E to that weight multiplies the odds. Now, how do we choose W and B? Not with least squares. Squaring the error of a squashed output gives a bumpy non-convex mess with almost no gradient when you're badly wrong. Instead, we ask a sharper question. Which weights make the labels we actually observed most likely? That's maximum likelihood. Taking its logarithm turns it into the loss we minimize, the cross-entropy or log loss. For a positive example, it's minus log p. For a negative one, minus log of 1 minus p. It's a surprise meter. Confidently right costs almost nothing. Confidently wrong costs enormously. The penalty shoots toward infinity. And unlike squared error on a sigmoid, this log loss is convex, a single bowl, so gradient descent can't get stuck. That's the whole reason we switch losses. There's no neat closed-form formula like there was for the straight line fit, so we roll downhill instead with gradient descent. And here's the payoff for pairing cross-entropy with the sigmoid. The gradient collapses to something stunningly simple. It works out this cleanly because the sigmoid has a lovely derivative. Sigma prime equals sigma times 1 minus sigma, and when you plug it into the cross-entropy, everything cancels. What's left is the push on each weight, the prediction minus the truth times the feature, p minus y times x. Look familiar? It's the exact same shape as the gradient in linear regression, where it was prediction minus truth times x. Same rule, different squashing. So the boundary line just rotates and shifts step by step, driven by that gradient, until the sigmoid separates the two classes as well as it can, and the log loss stops dropping. Let's make it concrete. Say we fit a model on hours studied, p equals sigma of 1.5 x minus 3. First, where's the boundary? Set the score to 0. 1.5 x minus 3 equals 0 gives x equals 2 hours. Below 2, we predict fail. Above, pass. Now predict for a student who studied 2.8 hours. The score is 1.5 times 2.8 minus 3. That's 1.2. Push it through the sigmoid, 1 over 1 plus e to the minus 1.2, which is 0.77, so a 77% chance of passing. And the odds? E to the 1.2, about 3.3, roughly 3 to 1 in favor. That's students on the pass side of the boundary. That's logistic regression, end to end. Before we wrap, 3 things that trip people up in practice. First, that 1/2 threshold is a choice, not a law. If missing a positive case is far worse than a false alarm, think disease screening, you lower the threshold and catch more, at the cost of more false positives. The model gives you a probability. Where you cut it is up to you. Second, a subtle trap. If your two classes are perfectly separable by a line, the fit tries to make the sigmoid infinitely steep, and the weights run off to infinity. The cure is regularization, a penalty on large weights that keeps them finite and the model humble. And third, the big limitation. That boundary is always straight. If the true split between your classes curves, the classic exclusive or pattern, plain logistic regression simply can't draw it. The fixes are to engineer smarter features, or to stack these units into a network that can bend the boundary, which is the perfect place to end. So, logistic regression in one breath. Take a linear score, wx plus b, squash it through the sigmoid to get a probability between 0 and 1. The score itself is the log odds, so the decision boundary stays perfectly straight. And we fit it by maximizing the likelihood of the data, minimizing cross-entropy, rolling downhill with a gradient that's just prediction minus truth times the feature. 2 quick roads from here. Swap the sigmoid for the softmax, and you handle many classes instead of 2. And notice, a linear score, then a sigmoid squash. That is exactly 1 neuron. Stack thousands of them and you've got a neural network, but that's a story for another video. Thanks for watching. This is Gradient Canvas, where we make AI beautiful and understandable. If you enjoyed this and want to understand AI concepts, please like, subscribe, and share it with others. Join us to explore more AI concepts from neural networks to transformers. See you in the next video.